Friends, today we start with the study of small signal stability. We shall devote our discussion toward the small signal stability of a single machine infinite bus system. That is, for understanding the concepts related to the small signal stability, we will consider a simple system, and that is a single machine connected to an infinite bus. Okay. The small signal stability is the ability of the system to maintain synchronism under small perturbations. The small perturbations continuously occur in any power system due to changes in loads and generations. Now, for analyzing the small signal stability of any system, the system model can be linearized around an operating point. That is, the disturbances are considered to be so small or incremental in nature, so that we can develop a linear model of the system around the operating point. Once we develop the linear model of the system, we can understand the behavior of the system under small perturbations, various parameters of the system which affect the stability of the system. Further, the moment we have a linear model, we can apply the linear control system theory for designing the controllers. Now, here when I talk about the controller, particularly we are interested in designing the excitation system control, that is the voltage regulator and the power system stabilizers. As we will see that in any power system, right, the actual system is somewhat complex. It is not as simple as a machine connected to infinite bus. It is always a multi machine system, right. Now, in any multi machine system, as you know that the system will have different modes of oscillations. The modes of oscillations are classified as local modes of oscillations, inter area modes of oscillations and the control modes. Okay. Now, primary requirement of the system is that this system should have, for stability, it should have positive synchronizing torque coefficient and positive damping torque coefficient. The stability of the system will be affected if any of these two torques or any of these two torque coefficients become negative. Okay. Now, to start with, we will study first a simple model considering constant flux linkages in the field winding. That is, we will first start with the constant flux linkage model. Next, we will include the field winding dynamics. That is, we will consider next step the constant field voltage, and once we assume this voltage applied to the field winding as a constant, okay, the model is developed so that we take care of the dynamics of the field winding, that is changes in the field flux linkages. This particular stage, when we say that the applied voltage is fixed, means it is practically a manual control. After studying this model with constant field voltage, we will extend it to the model which will include the automatic voltage regulator, and we will study the effect of the parameters of the excitation system and gain setting of the automatic voltage regulator on the stability of the system. Then the next step will be we include auxiliary controllers, that is the power system stabilizer. That is this, the stage by step development will give us the complete insight into the small signal stability problem. The system which we consider for small signal stability to start with is a machine infinite bus system, where a synchronous generator is connected to a large system which can be characterized by a infinite bus. The equivalent circuit can be represented as a generator. We represent the terminal voltage of the generator. The line is represented by an equivalent impedance Z equivalent equal to R e plus j times X e, and connected to an infinite bus, right. Now, here even in the multi machine system, right. Now, if you take out one generator and the connected line, right, then rest of the system if you represent by a infinite bus, then it becomes a machine infinite bus system. Now, as we continue our studies, to simplify our model and understanding, the resistance of the line or the equivalent resistance R e may be ignored. Now, when we consider classical model, that is, we assume the field flux linkages to be constant. Okay. Now, when we consider the classical model of the synchronous generator, then the synchronous generator is represented by a constant voltage behind direct axis tangent reactance, right. Now, here we will represent the voltage behind tangent reactance by the symbol E prime, and the voltage of the infinite bus as E b. Okay. And the phase angle between E prime and E b is denoted by delta, right, and that is the power angle of the system. Now, for this machine infinite bus system, we have derived earlier the power angle characteristic. Okay. The power angle characteristic to derive, we can start with the terminal current of the synchronous generator as the E prime minus E b. Now, here we are representing the voltage band tangent reactance, if it is represented as E prime angle 0, then you can consider this as an reference voltage. Generally, we do other way around, we consider the infinite bus voltage as a reference, and the internal voltage leads the reference voltage by some angle delta. Okay. But it does not matter very much. We can write down the expression for current I t. This is the first step for solving this problem, because what we know will be the whenever we start solving the problem, the terminal voltage of the machine will be known to us, right, and therefore, once the terminal voltage is known, we can find out the internal voltage by this formula E prime equal to E t o plus j times x t prime into I t o, where here now we denote this total reactance x t as x d prime plus x e. Earlier, the power angle characteristic which we derived was relating the terminal voltage with the internal voltage, but now here we will be deriving the power angle characteristic relating the infinite bus voltage with respect to the internal voltage. Okay. Therefore, the total reactance which comes will be x d prime plus x e. X e is the reactance of the transmission line. Okay. Then the complex power behind x d prime is given by S prime is equal to P plus J times Q prime, you can call it P prime. Okay. This is E prime into I t complex, or I am sorry, I t conjugate, right. That is, the complex power is P prime plus J times Q prime, and this is obtained by multiplying this voltage E prime by conjugate of I t. Okay. When you make these simplifications, you can write down the expression for air gap torque. Now, we all know actually that in case we neglect losses, right, then the air gap torque is equal to the power output in per unit system. That when you consider the per unit system, then the power output at the terminal of the machine is same as the air gap torque. Okay. And this is our standard power angle characteristic. Now, here at this stage I would like to mention that in case instead of having a non salient pole machine, if we have a salient pole machine, right, then the power angle characteristic will be different from what is given here. It will have another term which is known as the reluctance torque. Okay. And one can write down the expression for the power angle characteristic, but this is a primary requirement to start with. The next step is you linearize the expression for air gap torque around an operating point. Our initial operating condition is characterized by the angle delta equal to delta naught. That when you are operating and transferring certain amount of power, right, the initial value of delta is delta equal to delta naught. Okay. The linearized equation is written in the form delta T is equal to partial derivative of T with respect to delta into delta delta, because this expression is very simple. There is only the T e is function of one variable only here. We are assuming this E prime and E b constant. Okay. The infinite bus voltage assumed to be constant, the voltage behind transient reactance is assumed to be constant, the total line reactance is constant, and therefore, the torque is function of delta, only one variable, and therefore, when you obtain the small change in the air gap torque delta T is equal to partial derivative of delta T divided by delta delta into delta delta. Therefore, here basically this partial derivative becomes derivative term itself, right. There is no other, you can say, parameter on which the T depends. Okay. But in case actually these are also variables, right, then when I talk about this term, it is the partial derivative with respect to delta delta. When you take other terms also, then you have to take the partial derivative of this quantity with respect to not delta. See, when you take this partial derivatives, there are so many variables will be there. You have to keep on taking all the variables, then you will have delta delta, delta E prime, delta I prime like this. It is basically, it is actually the Taylor series expansion. We are trying to expand the equation around the operating condition, right. Now, we come to the basic equations of motion. We had developed earlier the swing equation of the synchronous generator, and the swing equation is a second order nonlinear differential equation. This equation can be represented by two first order nonlinear differential equations. It will continue to be nonlinear. These two equations are written here as P delta omega r equal to 1 upon 2 h T m minus T e minus K d delta omega r, and second equation is P delta equal to omega naught delta omega r, where delta omega r is the deviation of the rotor speed with respect to synchronous speed, right. The K d is the damping torque coefficient. For the sake of completeness, right, we include damping term also. Because earlier when we discussed, actually K d was not explicitly included in the equation, but the complete equation is in this form. Now, when the equation is written in this form, the speed deviation, the delta omega r is expressed in per unit. Delta omega r is expressed in per unit. The mechanical torque, electrical torque are also expressed in per unit. We know how to define the inertia constant h. The time in this equation, the time, instead of putting in per unit, we always prefer to express time in seconds, right, and therefore, the second equation has P delta equal to omega naught into delta omega r. Now, these are the two basic equations around which we will be developing this small signal model using these equations, small signal model, and studying the basic concepts of small signal stability. Now, what we do is that these two equations, that is 18.5 and 18.6, we will linearize around the operating condition. Okay. Now, to linearize this around the operating condition, one assumption here which we are making is that there is the mechanical power input remains constant, that is T m is constant, right, and T m is equal to the initial power output, that is T e o. Okay. And therefore, when we talk about the small perturbations, our equation will become P delta omega r equal to 1 upon 2 h delta T m minus K s delta delta minus K d delta omega r. This delta T m is considered to be a change in mechanical torque, okay, but generally this change is included in the model, to obtain the dynamic performance by giving a small change in the mechanical torque, right. Otherwise, the mechanical torque remains constant. This delta T term has been replaced by K s delta delta, and this term K s is synchronizing torque coefficient, right. And what will be the unit of this coefficient? Unit per unit torque per radian. Now, in this equation actually the delta delta is expressed in radians, electrical radians. Okay. Similarly, the unit for K d, the torque in per unit per radian per second.
So, in previous equation, P delta equals to omega naught into delta omega r. So, how this equation comes? Because P delta equal to I think omega naught plus delta omega r.
Now, if you see the basic equation, it is like this: d delta by dt
Yes.
is equal to omega minus omega naught, where omega naught is the synchronous speed. Okay. Now, what we do here is that this difference we denote by, in fact, actually this speed, actual speed is called omega r, the speed of the rotor. Okay. This will denote, this difference is denoted by delta omega r. Now, what we do is that we divide this by omega naught, so that this quantity becomes in per unit, and multiplied by omega naught, so that I can represent d delta by dt as delta omega r into omega naught, while this delta omega r is expressed in per unit. Okay. While in this equation, in this whole equation, delta is expressed in electrical radiance. Because when you solve these problems, we have to be very clear about the units. Okay. See, originally when you see the our swing equation, right, it is of the form d omega divided by dt, d omega r divided by dt 1 upon 2h divided by s, 2h divided by omega r, okay, equal to accelerating power. Okay. Now, here when I express this omega r in per unit, this is omega naught, not omega, this is omega naught, this is omega r, right. Then this term is combined here. Okay. So, that I have this coefficient equal to 2h only. That is when you write the equation in this form, 2h d omega r by dt equal to P A. Okay. Here this omega r is in per unit. Further, omega r can be represented as omega naught plus delta omega r. That omega naught is, in this particular case, when it is per unit, omega naught will become 1. That is, you can put this as 1 plus delta omega r. Therefore, when you substitute this expression here, I can write down the equation as 2 times h d by dt of delta omega r equal to P A. Is it okay? That is, since we know actually the derivative of this 1 is 0, therefore, d by dt of delta omega r is same as d omega r by dt. And that is why when you look at the swing equation which we have written here, okay, original swing equation, this is not a linearized equation, we can write down this delta omega r. Okay. Is it clear? Actually, these two equations are very important actually, because when you solve a given problem, right, it is very important to understand that how the quantities are expressed, what quantities are in per unit, what the unit of time, what is the unit of delta, what is the unit of speed deviation. All these terms are very important. Okay. Now, when you look at this equation, This is a equation in terms of small variations of speed, angle and mechanical torque. Okay? And therefore, we can take the Laplace transform of this equation, right. When you take the Laplace transform, it will become something like this: S times delta omega r s equal to 1 upon 2 h delta T m s, okay, minus K s times delta s minus K d times delta omega r s. That is, in this equation all these variables are the Laplace transform. Okay. And therefore, now what we can do is that we can write down delta omega r s as 1 upon 2 h times this whole expression. Okay. Now, this equation is represented in the block diagram form here. At this summation point, we have delta T m, K s times delta that is your delta T e, that is delta is here, delta T e, and K d times delta omega r. Now, when I represent this in the block diagram form, all these variables are the Laplace transform, but for the sake of convenience we may not write delta as delta with s, okay. But we understand that in the block diagram or in the transfer function model, all the variables which we represent, they are the Laplace transform of the original variables, okay. Delta T m also delta T m s. Therefore, this is the summation point where we derive a quantity which is given in this bracket delta T m minus K s delta minus K d delta omega. Now, this quantity when it is multiplied, now here it is 2 times H s. When you multiply this by this block 1 upon 2 times H s, right, we get delta omega r here. Okay. Now, the next step here is to linearize the second equation. Our second equation was P delta equal to omega naught into delta omega r, but this delta is our, or actually the delta can be written as delta O plus delta and therefore, P delta is same as P delta because delta O is constant. That is, if you take the derivative of this term, that is d delta by dt, right, then this comes out to be same as d delta by dt. Okay. Now, if you take the Laplace transform of this equation, then it will be s times delta s equal to delta omega r s into omega naught. Therefore, I can now write down delta s equal to omega naught by s into delta omega r s. Okay. Therefore, the speed deviation, right, is related to the angle deviation by this transfer function omega naught by s. Okay. And therefore, in this block diagram, this transfer function omega naught by s relates the angle deviation, that is delta to delta omega r. Okay. And therefore, this block diagram is is extremely important to understand the small signal stability of a power system, because we will be developing the complete model including additional blocks to this basic block diagram, right. Now, the next step to understand the whole thing is that we develop a characteristic equation of this system, right. Now, to develop the characteristic equation, we can make use of this block diagram and relate this output delta delta. This output delta delta is to be related to change in mechanical order. This is the input, right. Therefore, if you look at this block diagram, input is change in mechanical torque, output is delta delta. Therefore, this is a single input single output system. Okay. Then normally they call it SISO, single input single output system, and you can simplify this model and obtain a simple transfer function relating the delta delta to delta Tm. That is, first we write down what is delta delta as omega naught by S 1 upon 2 times Hs into this whole quantity, which is delta Tm minus Ks delta delta minus K d delta omega r. Okay. Now, in this equation what we do is that we replace this delta omega r by delta delta upon omega naught into S, right, because this relationship is there in the block diagram. You can see this block diagram relationship, delta delta is equal to omega naught by S into delta omega r, right. So, that when you look at this equation, we have now delta Tm, delta delta and other constant terms. Okay. And therefore, when you rearrange the whole thing, you can write down the equation in this form: S square delta delta plus K d by 2 h S delta delta plus K upon 2 h omega naught delta delta equal to omega naught by 2 h delta Tm, right. Now, when you equate this expression to 0, we get the characteristic equation for the system. This is the input term, right. Therefore, to obtain the characteristic equation, we can use this expression. Therefore, the characteristic equation is in the form S square plus K d by 2 h S plus K s omega naught by 2 h equal to 0. Since the system which we have considered is a second order system, therefore, characteristic equation is also a second order characteristic equation. Now, you can see here the coefficients are depending upon the damping term K d, the system inertia constant H, the synchronizing torque coefficient K s. Now, these are the system parameters. Further, you can easily see that K s depends upon the operating condition. Okay. It also depends upon the line reactance, because the expression for K s is for this single machine infinite bus system, the expression for synchronizing torque coefficient is E prime into E b divided by x t into cos delta O, right. And therefore, we can easily see here actually that in this characteristic equation the coefficients are function of loading, that is system operating condition, and system parameters also. X t depends upon the line reactance, similarly it depends upon direct axis tangent reactance, right. Now, when this equation is similar to our standard equation in this form, S square plus 2 times zeta omega n into S plus omega n square. and you can identify that this coefficient 2 times zeta omega n two times zeta omega n is equal to k d by 2 h. Similarly, this omega n square term, that is this term is equal to k d by 2 h, while this omega n square term is equal to k s omega naught divided by 2 h. Okay. Now, when you obtain the roots of this characteristic equation, right, the roots can be written as S1 S2 small s S2 equal to minus zeta omega n plus minus j times omega n square root of 1 minus zeta square. That is, in this case the roots will depend upon whether they are complex conjugate or real on the value of zeta. If zeta is greater than 0 and less than 1, right, we will get these two roots as complex conjugate roots. Right. Now, a system whose zeta is greater than 0 and less than equal to 1, right, we say that this system is underdamped. A system whose zeta is equal to 1 is critically damped. And a system whose zeta is greater than 1 is overdamped. Right. And a system whose zeta is less than 0 is unstable. It has a negative damping, system is unstable. Right. In any system, we have to ensure that the damping is adequate, so that the oscillations which are generated are damped out. Whenever we design the controller for the system, we have to achieve certain minimum damping for all the modes which are present in the system. Right. Now, here we can also give some more interpretation to the damping term zeta. That is, if you plot these roots in the S plane, then assuming that damping zeta is positive, the roots will appear in the S plane, because here we show a real part, we call it sigma, we call this as omega on this axis, and any root is written as sigma plus minus j omega. Right. Now, if the system is a stable system, like having its complex conjugate or the roots lying in the left half of the S plane, then this term, that is, this can be written equal to how much, zeta omega n, while this term will be equal to how much? Omega n square root of 1 minus zeta square. What will be this quantity? Omega n. Therefore, this omega n is the distance of the root from the origin. Okay. Now, if you find out this, if you look at this angle theta, right, then cosine theta is equal to zeta, right. Therefore, whenever we perform this eigenvalue analysis of the system, we can draw in the S plane a line which will represent certain value of zeta. That is, you can that is, suppose this is your S plane, right, and if I say that this line represents zeta equal to say 0.1, this line will represent zeta equal to say something more than 0.1, 0.2, like this. Now, in case all the roots lie on this side of this line, it means each mode or there is no mode whose damping is less than 0.2, right. Therefore, whenever we design the control for this for improving the system stability, particularly the AVR tuning or power system stabilizer tuning, right, we perform the root locus analysis, okay, and vary the parameters like gain setting and see actually that you get the optimum performance, but at the same time you ensure actually that no root is having its damping less than the desired value. That therefore, this is a very important way to ensure that we do not go to a stage where any of the roots is less than or any of the roots is having its damping less than desired value. Okay. Now, for this system which we are considering here, the omega n is the natural frequency of oscillation. It is given by this formula omega n is equal to square root of k s omega naught by 2 h, and the damping ratio zeta is 1 upon 2 times k d divided by square root of k s 2 h into omega naught. Okay. These two terms you can derive and see that you get the value of omega n and zeta like this. Now, the next point which we will study is see this the two differential equations which we have derived, the linearized differential equations. One differential equation was written in this form. Okay. Similarly, we had written second differential equation in the linearized form. Okay. Now, you can arrange these two differential equations, right, and write the model in the vector matrix form. That is, for analyzing the stability of the system, right, the most convenient form of representing the model is vector matrix form. That is, we write the model in the form of x dot equal to a x plus b u. Right. Now, these two equations which we had derived can be arranged in this form, that is d by dt of delta omega r equal to minus k d by 2 h delta omega r minus k s by 2 h delta delta plus 1 by 2 h delta T A. Second equation is d by dt of delta delta equal to omega naught into delta omega r, that is all. Okay. Therefore, these two equations which we have derived can be written in the vector matrix form, and when we make use of the say MATLAB for analyzing the system performance, right, then we can find out the eigenvalue of the system matrix A, right, for studying the stability characteristic of the system, right. Now, we have to understand very clearly here that this matrix A is function of operating condition and system parameters. This I will be emphasizing again and again here, that whenever you write down the model in the form x dot equal to x plus b u, right, then the basic stability characteristics are determined from the system A matrix. Okay. Therefore, let me summarize here that what we have done till now is we have developed the small signal model for the machine infinite bus system, and we have represented this model in the form, that is vector matrix form x dot equal to x plus b u. We can write down the A matrix, we can write down the B matrix, and the state variables in this model are delta omega r and delta delta. They are the state variables, while delta T m in this case is a input. Okay. Now, I will just give you one more important information, that was the importance of this term 2 h. Okay. Now, to understand this importance of this term 2 h, let us look at our swing equation again. Our swing equation is d by dt omega r equal to 1 upon 2 h T A, okay, where omega r is expressed in per unit. Okay. Now, suppose you have a synchronous generator and which is at steady state, 0 speed, okay, and if you apply the rated torque, then in how much time the synchronous generator will attain its rated speed, right. Now, to obtain the time in which the synchronous generator will attain its rated speed can be obtained by integrating this equation. That is, you integrate this equation, assume T A equal to 1 per unit, okay, T A equal to 1 per unit, and just tell me quickly in how much time the synchronous generator will attain its rated speed. Okay. The synchronous generator will attain its rated speed starting from 0 to its rated value when it is applied with a rated accelerating torque, that is T A is equal to 1 per unit, and therefore, this time 2 h is also denoted as the mechanical starting time of the synchronous generator, that is T m is equal to 2 h. Therefore, if you see in the model we have a term 1 upon 2 h, therefore, this 2 h is similar to a time constant and is the mechanical starting time of the synchronous generator. In literature you will find actually that many times we represent this term, this T m, by a symbol capital M. That is, you will find actually when you read the literature that this block 1 upon 2 times H s is also represented as 1 upon M s. Now, here we should not get confused with the term M, the angular momentum of the rotor, right. The M here is actually in this model will be equal to 2 h, and which is the mechanical starting time of the synchronous generator rotor when it is subjected to a rated torque. Similarly, if the machine is running at constant speed or rated speed and if you apply a retarding torque equal to the rated torque, then its speed will come down to 0 in a time equal to 2h, right. That also gives the information that how much time the machine will take to retard from its rated speed to 0 speed. Therefore, with this today I will conclude my presentation by saying that we have developed a linear model of a machine infinite bus system considering constant field flux linkages. Okay. We have also studied the importance of damping ratio zeta, right, and whenever we design the system, right, the zeta is going to be one of our design parameters. Okay, thank you.